Okay, so I keep it short. Now we have three speakers in this session. The first is István, the pinning down number and cardinal arithmetic, please.
Okay, thank you. Well, first of all, I'd like to thank the organizers, especially because they invited me for this very special event of celebrating Mirna. I first met her, well, I don't remember the year, but it was sometime in the late 90s. We were both visiting Saharon, and so we stayed in the same apartment, and she cooked a great dinner for us, steaks then. And then we have met many, many times. She has been always very nice to me, so I am really honored to be able to talk on this special occasion. Yeah, also I guess our interests are very close, so I hope the results I'll talk about she'll take as a substitute birthday present. Yeah, this whole event here at the Newton Institute is about set theory and its applications in many fields. And of course, general topology or point set topology, or the way I like to call it, set theoretic topology, is one of the basic areas where set theory is applied. I mean, already Cantor they had important contributions, but then Hausdorff, who is, of course, after whom the prize of our society is named, is really maybe one of the founders of set theoretic topology. And his book, his very basic book on set theory, has a lot of material about topology. Actually, I think the first really modern definition of a topological space is due to Hausdorff. It's actually not, they are called Hausdorff spaces, but if you just leave out the Hausdorff separation axiom, you get the general notion of topological spaces. Now, these topological spaces are very, very simple objects from the point of view of set theory. So those of you who are not very familiar with topology, I don't think you will have much problem understanding what I will talk about. But if you do, please stop me and raise your hand and ask what you don't understand. Okay, so I guess first I would have to tell you what the spinning down number is, because this is a relatively, I mean, the notion is again very simple. Okay, the pinning down number of a topological space X, PD of X, is the smallest cardinal kappa such that for every neighborhood assignment, what's a neighborhood assignment? Well, it tells you what it is. You assign a neighborhood to every point of your space. Okay, so in fact, usually it's an open neighborhood, but it doesn't make much of a difference. So the minimal kappa such that every neighborhood assignment can be pinned down by kappa points, which simply, of course, means that there is a subset of X of size kappa which intersects every member of the neighborhood assignment. Okay, I guess this doesn't need too much of an explanation. Of course, you have what's called, and it was already mentioned several times in this workshop, that you have the density of a topological space. That's the pinning down number for all the open sets. In fact, for all the non-empty open sets, but I will probably not always. When I say open, I usually mean non-empty open. Okay, for neighborhood assignments, you don't have to say non-empty because they are non-empty by definition. So. Okay, so this is a kind of a local version, and I'll talk about this. Now, Orici and Bella, about 2 years ago on the archive, they introduced this cardinal function. They called it completely different, and they didn't do very much of it, but they had sort of a general theme, namely for any cardinal function. They didn't, I mean, this is behind what they did in that paper, but it's obvious. For any cardinal function, okay, they are also sometimes called cardinal invariants of, you know, like the density or the weight, which was mentioned earlier, or pi weight, or etc. Lots of such functions which assign cardinal numbers to topological spaces. Usually, you like for the density, you define them for all the open sets. Now you sort of adopt whatever that means, but that should be always obvious. You adapt that from all open sets to neighborhood assignments. And this way you get a neighborhood assignment. So if phi was such a function, then phi sub na is the neighborhood assignment version. And of course, the pinning down number is just the neighborhood assignment version of the density. And when I was here in October, there was a meeting of mathematical biologists, and so I'll talk about DNAs, but I call them. Okay, I think the pinning down number, I don't know, I like this name. I invented that, so I take responsibility for it. Now, it's obvious that in general, the neighborhood assignment version is less than or equal to than the original version of a cardinal function. And for the pinning down number, it's obvious that it's greater or equal to than the cellularity. That's the supremum of sizes of disjoint families of open sets. Because if you have a disjoint family of open sets, you can assume they are part of a neighborhood assignment, and you need at least as many points to pin them down as they are, because they are disjoint. So this is obvious. A little bit less obvious, and this is basically what Orici and Bella proved. Oh, I'm sorry. That, okay, the character of a topological space is the supremum of the characters of the points, and the character of a point is the smallest size of a neighborhood base. So this is very simple. It's a very simple exercise to prove this, and this is basically what Orici and Bella proved. I mean, well, of course, this last inequality implies that if the character is less than or equal to the density, like if your space is first countable, then the pinning down number is just equal to the density. Okay, now in a much, you know, well, earlier in March, I mean, from the archive codes you can read off when they were they appeared on the archive. So these two mathematicians from the Ukraine, they also invented independently of Orici and Bella this concept, and they actually also had a general theme. They have quite a long paper, but very, very general things. But in the last section of the paper, they look at this, the pinning down number. Again, they call it completely different, and they use different notation. But they already proved something quite interesting there. Okay, the first thing they prove, basically they have two results. One is that if your space is, any topological space is small, it's less than Aleph omega, okay, whether that's, I mean, for us, this is small, but I mean for us theoretic topologies. But so anyway, this is quite surprising, and it's not trivial. I mean, unlike that, what Orici-Bella result, this is not terribly hard, but it's not trivial at all. And they also prove that if kappa is any singular cardinal, then they can construct a T1 space. A T1 space is such that singletons or equivalently finite sets are closed. So this is weaker than Hausdorff. Then they have an example of a T1 space whose pinning down number is the cofinality of kappa, while the density and the size of the space is equal to kappa. So in particular, oh no, and one more thing, if they also have that this, for this singular cardinal kappa, we have that 2 to the 2 to the cofinality is bigger than kappa, then they can make this example even Hausdorff. And their construction is pretty, especially the Hausdorff one is pretty complicated. Anyway, this shows that, first of all, one shows that the first result there is sharp, because for kappa equals Aleph omega, there is already a counterexample. It's only T1, but it's a counterexample. And consistently, they can even give Hausdorff example. Of course, even for kappa equals Aleph omega, but it works for any singular cardinal. Now, when I saw these results, and they also raised, by the way, two very, very natural problems. Once you see these results, okay, they ask, they have a consistent Hausdorff example, do you have one in ZFC? And also, Hausdorff spaces are nice, but regular or T3 spaces are even nicer. In fact, that's where topology really begins. Hausdorff spaces are really set theory in regularity. Okay, that's when topology really comes in the earnest. So these two natural problems were raised by them, and I was lucky to read their paper, and I immediately got very interested. I think anybody who is set theoretically minded would agree that these are really interesting questions. And I hope to show you that the answer is even more interesting. Okay, now, however, before I go to the answer, I mean, I'll give you a full answer to both questions, but first, some results that I think are interesting. And all the results that I'm mentioning here, I guess, not very surprisingly, this is the due to his joint work with Lajos Sokub and Zoli Szentmiklósi, our standard group in Budapest. Okay, and our paper appeared on the archive just 3 months after, and it will appear in the Israel Journal. It was accepted within like a week or something. It never happened to me that. So I suspect that this is a good paper. Okay, now here is a little definition. It's not really a definition. It's a piece of notation that given this tau plus of x denotes the family of all non-empty open sets. Okay, the family of all open sets is the topology, and the non-empty ones that we are interested in. Okay, and for every space, of course, you have this. Okay, you can define the smallest size of a non-empty open set, and here is a proposition which is sort of implicitly contained in the Banach-Rafsky paper. It's not terribly difficult, but it's important and interesting. It says that if you have a space such that the pinning down number is different from the density, then you have a open subspace Y of that space X, which is also an example of where the pinning down number is different from the density, and in which all non-empty open sets are of the same size. And such an example, I mean, by example I always mean a space where the pinning down number is different from the density, and the canonical examples are where you also have this homogeneity of all with respect to cardinality. All open sets, non-empty ones, of course, have the same size. By the way, not surprisingly, since any example gives you a canonical one, the Banach-Rafsky examples, if you look at them, they are canonical. All right, so one result, this is just to show that if your space is nice, okay, locally compact spaces are nice. I think David would agree that they are. So for them, okay, the pinning down number is always equal to the density. This is not terribly hard. Much more surprising and much harder is the following result, that one has this inequality for every Hausdorff space. We have that the double exponent of the pinning down number is an upper bound for the size. Without the p, so with the density instead of the pinning down number, this is a well-known classical result from the 1930s of Pospisil. I mean, at that time, I guess this was, I mean, nowadays this is a triviality, but then it was a published result. And it turns out that you can replace density with the pinning down number. Of course, if they are equal, then this is not very surprising, but you can always, there is no assumption here for Hausdorff spaces, and we know that at least so consistently you can have Hausdorff spaces where the pinning down number is strictly less than the density. So this is a strengthening of this Pospisil inequality. And one more interesting part of this theorem is that if we have an example of a space where the pinning down number is less than the density, then its delta is actually strictly less than this. So in particular, For canonical examples, of course, you have here the size, because then so it shows somehow that canonical examples are interesting. Well, anyway, so these are some interesting results mainly for Hausdorff spaces. And now for regular spaces, okay, once we proved, I mean, that strengthening of the Pospisil theorem, we went to regular spaces, and of course everybody who knows a little bit about satiric topology knows that the weight of a T3 space is less than or equal to 2 to the density. And it is actually because the number of all regular open sets is less than or equal to. This is very standard, and this is, unlike Pospisil's theorem, this is really trivial. So, but it was natural to ask if you can also replace the density with the pinning down number in this inequality. And this is a problem. We don't know. So this is open. So we have no idea. It looks like it's a very hard problem, but we could give some partial result. So for every regular space X, we have, well, not the weight, but the minimum of delta and the weight less than or equal to 2 to the PD. So this is partial result. And we also could prove for regular spaces that the density is always less than 2 to the PD. Now, of course, under GCH, this gives you that, okay, in that case, 2 to the PD is PD plus. So if something is less than PD but greater than or equal to that, has to be equal. So this already shows that cardinal arithmetic and, okay, the spinning down number are somehow connected. And we'll see more connection later. Moreover, there is also this result that if X is an example, okay, for pinning down less than density, then the delta will be less than 2 to the PD. Okay, this is very similar to what we had in the previous slide, but there we had double exponent, but for Hausdorff, and this is for regular. So a canonical example, you have that the cardinality is strictly less than 2 to the PD. Okay, and now I hope I could show you that there are interesting things you can prove about PD, and let's solve the problems of Banach and Rafsky. All right, so I define weak GCH. It's a very simple statement. It says that for every kappa, 2 to the kappa is a finite successor of kappa. It's a natural statement, but actually we used it with Zoli Szentmiklósi in a paper about 10 years ago, but I've never seen it anywhere. I think it's a natural assumption, and it will come up. I mean, so far this has no topology in it. And of course, if you think a little bit about this, you'll see that this is also equivalent to the statement that every limit cardinal is strong limit. Okay? All right, and now our first main theorem says that the following, I'll have 3 statements are equivalent. First, that the pinning down number is equal to the density for every Hausdorff space X. Okay, well, that's a statement. And Banach and Rafsky asked if this can be proved, or if this is false in ZFC, because consistently this is false. Okay, the same statement, but with 0-dimensional added. And of course, well, all you have to know now is that this implies T3, in fact, much more so. 0-dimensional means that you have a base consisting of clopin sets. So those are regular open, and so such a space is regular. And the third statement is weak GCH. So this really answers both questions of Banach and Rafsky, because it shows you that, of course, you cannot have of course, weak GCH is consistent, and so in that model you don't have Hausdorff counterexamples. And actually, the existence of Hausdorff counterexamples of 0-dimensional Hausdorff, and therefore of T3 examples, are just equivalent. Okay, so this really gives you a full solution of those questions that Banach and Rafsky raised. All right, so I'll tell you the proof is not easy or simple, but I give you some ideas how it goes. So here is a theorem. That's ZFC, I mean, no assumption. But of course, what does it say? It says that if, it says that if mu is a strong limit cardinal, doesn't say singular, it's just strong limit. And you have a space with this homogeneity property, that all open sets, non-empty ones, are of the same size. And this common cardinality is a finite successor of this strong limit. Then for such a space, I'm sorry, I didn't emphasize that this is for Hausdorff spaces, then the pinning down number is equal to the density. And what I already, this yields the arrow from 3 to 1. Because if you have weak GCH, okay, all limit cardinals are strong limit, and every cardinal is a finite successor of a strong limit cardinal. Okay, so you have that so you have that there are no canonical counterexamples, but if there are no canonical counterexamples, then there are no counterexamples at all. There was that proposition that every example gives you a canonical one. Okay, any question? So this gives you 3 implies 1. Of course, 1 implies 2 is trivial. So we still have to see, we still have to see how 2 implies 3, but before that I mentioned that in the case, okay, omega is a strong limit cardinal, so finite successors of omega, in that case the proof doesn't use Hausdorff. So we get, this gives you in particular a proof of the Banach-Tarski result, that if the cardinality of any space is less than Aleph omega, which means it's a finite successor of omega, then you have PD equals D. All right, so now a little detour. Well, we actually solved those problems, but on the way we came up with some other problems. But also, I still didn't tell you anything about this the implication 2 implies 3. But as you will see, it makes sense to make a little detour now. So, reg denotes the class of regular cardinals, and if mu is any singular cardinal, then this S of mu, so this is just notation, it's my notation. You look at all sets of regular cardinals below mu of cardinality, cofinality of mu, whose supremum is mu. Okay, so look at all these sets, and for any such set, for any element of S of mu, look at all the ultrafilters on A which contain all finite segments of A. Okay, this is just notation, but here is an important definition of Shalach. If mu is any singular cardinal, then he denotes by pp of mu, and that's short for pseudo power, is the following thing. You look at all ultra products with respect to these ultrafilters, which these are linearly ordered sets, so they have a cofinality, and look at the supremum of all these cofinalities. That's what Shalach calls the pseudo power. And well, one reason you call it is because it is between, it's, of course it's bigger than mu, but obviously less than or equal to mu to the cofinality of mu, which is sometimes called gimel of mu, but I don't know how to write gimel, so. But anyway, it's not. And here is the famous Shalach's strong hypothesis that this, okay, this is a very weak version of, I don't know, of singular, well, it has, all right, so now I don't know enough to really, but,
correction.
yeah?
Your S mu should be the set of A's which got order type mu rather than, order type cofinality mu rather than cardinality. Get into trouble.
Lajos said that this is what I thought, but so he read Shalach and he claimed, I don't know. So anyway, it's I don't know.
You have segments.
Yeah, I know it's different, but I don't know if you get the same thing. But Lajos told me this is, so I don't know. So anyway, this is not so terribly interesting, well, because as you will see, what is the actual definition. What's interesting is this strong hypothesis of Shalach, which says that the pseudo power is always the successor of mu for any singular cardinal mu. Okay. And now, okay, well, somewhere we have to construct, like from the assumption that the weak GCH fails, then we have to construct an example of a space. But so here is the construction theorem. And it will be used not just in that first main theorem, but I will have a second main theorem. And so that's why, I mean, I have extra parameters in the construction which I'll need there. Well, actually, so we have a singular cardinal mu, which this lambda shows is not strong limit. So, okay, you just look at mu and lambda, then this lambda is a witness for the fact that mu is not strong limit. And of course, if mu is not strong limit singular, then there is such a witness which is greater or equal to than the cofinality. If anything has power that jumps over, then everything bigger jumps. So if you only look at mu and lambda, this just says that you have a singular cardinal which is not strong limit. That is, you violate, they violate the weak GCH. And we also have, as I said, other parameters. We have this sigma less or equal to mu, and we have a rho greater or equal to mu, but strictly less than the pseudo power. Both of them can be equal to mu, and then they disappear. But one more assumption is that sigma, if sigma is not equal to mu, then it has to be regular. Of course, if it's equal to mu, it cannot be regular because mu is singular. Okay, so suppose we have this state of affairs. Then there is a zero-dimensional Hausdorff space X such that first the pinning down number is at most lambda. Second, the density is equal to sigma, which is bigger than lambda. So this is an example of the disagreement of P, D, and D, and that's what we want. In fact, it's even a zero-dimensional Hausdorff that we wanted. And it is a canonical example of size rho. Okay? So obviously it's a corollary. If you make both sigma and rho equal to mu, they disappear. You get a zero-dimensional Hausdorff space whose pinning down number is less than the density, which is equal to mu, which is equal to the cardinality, which is equal to the delta. So clearly this completes the circle in that equivalence, because that gives you the 2 implies 3, and that was only missing. So that, of course, I didn't give you the proof of the construction theorem. That's pretty hard, but okay, modulo that we have and modulo that previous theorem, we have this. Also, if mu happens to be a witness for the failure of Shelley's strong hypothesis, then you can take rho to be mu plus. And then we have a canonical example of regular even successor size. All right. So now the second main theorem, and observe the C here. The following are equiconsistent. Okay. We don't know, and I don't think there is equivalence, but we have the following equiconsistency. First, Shelley's strong hypothesis fails. That there is some singular cardinal mu whose pseudo power is bigger than its successor. Okay. Second, there is a zero-dimensional Hausdorff space X, which is a canonical example of regular size. Okay. And third, there is any topological space, not only its Hausdorff, any topological space which is a canonical example of regular size. All three statements are equiconsistent. Okay. Now, whether it's not so shocking that you can have a cardinal arithmetic statement like Shelley's strong hypothesis fails, and some topological statements that are equiconsistent. But here we have two topological statements. One, I mean the same statement for zero-dimensional Hausdorff spaces and for all topological spaces. We know they are equiconsistent, but we have no idea if they are actually equivalent. It's very strange, but okay. So this is another big open problem. All right. So yeah, I have time, I guess. So I can tell you something about the proof. Okay. So let's see first that the consistency of A implies the consistency of B. Of course, this will use the construction theorem, obviously. Well, if the witness mu for the failure of SSH is not strong limit, then okay, maybe I just go back. Then the construction theorem allows you to put rho equals mu plus, because mu plus is greater than satisfies this is exactly what being a witness for the failure of SSH is. And then the theorem just gives you exactly what you want, because you will have here mu plus. So you will have a canonical example of regular size. Okay, so this is if the witness for not SSH is not strong limit. What if it is? Well, this is where consistency comes in. Then you can do forcing. Okay, I use Kuhnen's notation. So actually, you put, instead of 2 to the mu, this 2 to the CF mu plus times 2 to the mu, and you add that many subsets, and that makes mu not strong limit, and you can show it remains a witness for the failure of SSH, and then we are back. We can use the construction theorem and get, so at least consistently get an example for what we wanted. Now to complete the circle, we have to go from C to A. It would be enough to go from the consistency of C to the consistency of A, but actually we, as I gave it away, one can show that actually C implies A. Modulo that Saharon is right, because we'll use his result. Okay, so here is what we prove. We prove that for any topological space which is a canonical example of regular size, okay, so we have the pinning down number less than the density, and all non-empty open sets are of the same size, which is regular. Then you can find, if this is the case, then you can find a singular cardinal mu below the size of X, and some lambda, cardinal lambda below the density of X, such that if you look at subsets of lambda, subsets of mu of size lambda, partially ordered by inclusion, then the cofinality of that is bigger than mu plus. Okay, so from the topological statement you get this. Well, first of all, this theorem gives us again a proof that if the cardinality of any space is less than Aleph omega, then PD equals D, because below a cardinal which is less than Aleph omega, there are no singular cardinals. So, okay, so that's just okay, it's a curiosity, but by a deep result of Shelah from PCF theory, if we have such mu and lambda, then SSH fails. Now, it doesn't say that this mu will be the witness. It just says that there is a witness. So maybe it's another. Now, Menahem perhaps knows how this goes, but I don't know. We were very lucky because we only had to quote this result. I mean, this of course tells you that, okay, if I go back, that if there is such a topological space, then we know that Shelah-Strong hypothesis fails. So that's actually C implies A. Okay, and I repeat that if you are interested on the archive, you can find the paper. And thank you for the attention, and happy birthday to Mirna.
Now we have some time for questions and comments.
Yes?
Well, first of all, thank you for the gift. It's lovely. And for the talk. Have you studied these other local verses? Do you think they're similar to?
I forgot to mention that we are just in the process of doing that. And for the weight and the pi weight, we have some interesting results, but nothing as nice as this so far. So, but we are following the general theme because we think, I mean, after this, we think that this might lead. But of course, you never know beforehand what's interesting and what is not.
Well, I know you probably we don't have time, but could you still give us a hint about the construction theorem? You know, what type of space you construct? Okay, if it's too much. Okay.
Well, yeah, I can tell you something. Now, maybe not the full version with the forget about the ultrafilters. So we just have a singular cardinal which is not strong limit. Okay, so we have. So let's see. Well, you can. Okay, you have. These are the, I don't know, kappa alphas that go up to mu, and you look at the product, but the topology is okay. So you have this lambda less than mu, such that 2 to the lambda is bigger than mu, and of course it's also at least as big as the cofinality of mu. And so this gives you that that there are on lambda. Okay, so we actually can assume that these are bigger than lambda. Of course, start later. And so we have on any such set we have independent sets 2 to the lambda, so that many as they are. So we break them up into that many. Okay, so this is kappa 0, then kappa 0 many kappa 0 places, and in each one we copy this independent collection, and okay, so we have functions that which is a scale, and so we also involve those, and that's how you define the topology, but the details are, of course, tedious. And when we have the ultrafilters, then they also come into the picture. Okay, and so if you have an ultra product which is bigger than the pseudo part, bigger than mu plus or that rho, then you can deal with the things of. So you can make sure that all the open sets will have size rho. I know it's not. It's I don't know, maybe a 10-page construction, so it's not easy and very technical. But I think you can. I mean, this product tells you the scale that you. It has things to do with PCF. Okay.
Yes, sir.
Yes.
Could you go back a couple of slides to the main theorem, ABC, the equiconsistency?
Yeah.
Yeah, so when you got from A to B, the first case was when you were assuming that this witness was not a strong limit. So this is important for your construction. Is there any kind of connection with Shell's strong hypothesis? Perhaps if you only assume Shell's strong hypothesis for singulars which aren't strong limits, is that connected with Shell's not so strong hypothesis, or?
No,
because if you assume that you have a failure for mu is not a strong limit, then you get A, B, and C are all equivalent.
Yeah, I think I should go back to the construction theorem. I mean, there it's essential that mu is not. I mean, the lambda is a witness. I mean, it's an assumption of the theorem that mu is not strong limit.
Sure. I'm just wondering whether is there a connection between Shell's strong hypothesis and Shell's strong hypothesis only when restricted to non-strong.
I'm sorry. I see. I don't know. Ask Menachem.
Because
this is something we wondered about.
Oh, you can have a counterexample to Shell's strong hypothesis without, and the counterexample is not strong limit. I mean, simply, if you have a counterexample, take the continuum, blow it up above this whole thing, it stops.
Yeah, that's what we did.
Yeah.
But of course, it would be nicer if you would, if you could.
Coin forcing doesn't change any of the PCF structure.
Yeah.
I was just curious because if you assume if mu was not a strong limit, then all A, B, and C would become equivalent instead of.
Yeah, that would be nice.
Maybe both.
I don't actually believe that there is equivalence, but I agree this would be nice. But we don't even know if the two topological statements are equivalent.
Yep.
Okay, let's thank István again.